Hello viewers and my dear students. Welcome to problem 7 on analysis of beams. This is session 1. In this session 1, I'll be giving you a demo on simply supported beam analysis with T section. Okay, please understand this is simply supported beam analysis. So far we are doing rectangular sections and all that. Now it has a T section. It's a different type of problem altogether, and please observe. And you have a transverse pointed loads on the flange using Ansys Mechanical APDL to obtain bending moment and shear force diagrams. Okay, the problem is this. As you see here, a beam has a T section. See here, this is a beam. Span length is 4 meters. Okay, 4 meters. And you have one pointed load at 2 meters from the left support and another pointed load at 3 meters from the left support. 15 kilonewtons and 20 kilonewtons. And if you take any section here, this is not if you take any section here, so far it used to be a rectangular section. Now if you take a section here, it looks like a T section. Okay, this is the flange, this is the web. Okay, now this flange is 120 by 10 and this web is 150 by 10. Okay, this you have to remember. Okay, 120 by 10 is the flange, this is 150 by 10. Okay, this is the problem. When this is the pointed loads are applied this way on a T section, okay, how the bending moment diagram and shear force diagram will appear. Here in the session 1, I will be concentrating only on bending moment and shear force diagrams and verification using Ansys. But in the session 2, I will be covering bending stress diagram, which is very important, very useful and all that. Okay. See here, to find reaction at the support. See here, RA, let us say this is the beam with T section. Okay. Okay, now you have reactions, no? RA plus RD is 15 kilonewtons, 20 newton, 15,000 plus 20,000, you write 35,000. Taking moments about A and all that. RD into, I have taken everything in millimeters. Okay, RD into 4,000 minus 20 into 3,000 minus 15 into 2, that is 2,000. In that way, I'll get RD as 22,500 newtons. Then once you substitute here, RA will get it as 12,500 newtons. Okay, this is the reaction. What you get, RA and RD. You remember, RA it is 12,500 newtons and RD it is 22,500 newtons. Okay, this is the reactions at the support which you have to remember. Okay, now this is the thing, and you have a complete T section 120 by 10 mm. This is 150 by 10 mm and all that. Okay, now once you get this, see here, this is 12,500 we have got, this is 22,500 we have got, and you see here to find shear force diagram, shear force between C and D, to the right of it you see, it is 22,500, upward is always positive, in that way 22,500, between B and C, 22,500 minus 20,000, okay, shear force between B and 22,500 minus 20,000 is 2,500 newtons. Okay, this is 2,500 newtons. Then shear force between A and B is all right forces you calculate. 22,500 minus 20,000 minus 15,000. Okay, 22,500 minus 20,000 minus 15,000 minus 12,500 newtons. This is the shear force diagram what you should get using Ansys. Okay. Now you see here in the same way, the bend you have the RA as 12,500, RD 22,500, which you already calculated. Bending moment at anyway D is 0. Bending moment at C, always clockwise moment you take it, anti-clockwise moment you take it positive. Bending moment at C, 22,500 into 1000, it is 2.25 into 10 to the power 7 Newton millimeter, because all I have taken it in millimeter. Okay, to 22,500 into 1 meter, 1000 mm are converted. Okay, bending moment at B is 22,500 into 2000 minus 20,000 into 1000. You see here, 22,500 into 2000 minus 20,000 into 1000. That is 2.5 into 10 to the power 7. And bending moment at A anyway is 0. That is the bending moment diagram. 0, 2.25 into 10 to the power 7. And this is 2.5 into 10 to the power 7 Newton millimeter. That is bending moment, you should know correctly this bending moment diagram. The maximum bending moment is occurring at B. That is 2.5 into 10 to the power 7 Newton millimeter. Same way, same thing you should get it using Ansys also. Okay, now what you do is, we'll go to Ansys. We'll go to Ansys. As usual, you change job name. Gurdat beam with T section I have given. You say yes and all that. Gurdat beam with T section. You change the title also. Change the title, and I've changed the title beam analysis. I've given here beam analysis with T section, concentrating only on bending moment and shear force diagram for the time being. Now once you do this, you go in the same way. Preferences, structural, okay. Okay. Preprocessor, element type, add, edit, delete. Add, edit, delete. You just say add. Say beam 2 node 188 only you take. Okay, say. Then close. Then material properties you go. Under material models, structural, linear, elastic, isotropic, you take it 2E5. Okay, and 0.27 you take. Okay, 2E5 is, that is 2 into 10 to the power of 5 Newton per millimeter square. Okay, because now it is Newton per millimeter square, the modeling should be in millimeter and the loading should be in Newtons. 2E5, you take it as 2E5 and finish it off. Okay, just say okay. Then material, exit you do. Then section you go, beam, common section you go. Here you be careful. Beam common section, beam ID let us say 1 here, and you take T section here. T section you take it here, and width 1 as you see here in the problem it is, if you observe, it is 120. Width 2 from here to here is 150 plus 10. It is up to here it is 150 plus 10. 160 you take. 160 you take, and thickness is 10 mm and 10 mm. Okay, this you be careful here. This you have to be careful here. This is W1 120. This is flange length. Width is actually 150 by 10 plus here what they are given is width plus this thickness, flange thickness also they are given W2. That is why I given actually 150 plus 10, 160. In that way, if you do, you can just see mesh view. If you see here, this you can go. You can go for coarse mesh or for fine mesh and all that. Okay. Can you follow? This mesh view, you can make the coarse mesh and all that. These things we'll do anyway in the next session. Okay. This, if you see here, everything, it automatically calculates area, that is moment of inertia about YY and IZZ, everything we'll do it in the next session. Okay. This you just say okay. Okay. Then you go for modeling, create key points in active coordinate system. Then 1 you take 0, 0, 0 you take, apply. Then 2 you take, 2 is 2000, 0, 0. 3, 3000, 0, 0. And 4, 4000, 0, 0. Okay. That means you have 4 key points. Now you create lines there. Create lines, straight line, connect 1 to 2, 2 to 3, 3 to 4. Just say okay. Okay. Once you've done this, then you go for meshing, mesh attributes, picked lines, pick all this. Okay. Just say okay and take the default attribute. Don't worry about the key orientation point. This is only for the next one. When you want beam stressor, that is bending stress and all that, you have to rotate the beam by 90 degrees, then it is required. Now for bending moment and shear force diagram, orientation, the rotation is and all that is not required. That is why I'll not go. Just take the default values. Section is 1, beam 188, material is only 1, everything you take the default values only. Okay. Then you see a size controls, manual size, lines, picked lines. You take this, and make it okay and say 25 divisions, let us say 25 divisions if you make it. Okay, if you see here 25 here, 25 here, 25 here, in that way if you do this mesh lines pick all, if you do, you get 75 elements. Now you see here list elements, if you just go, okay, 75 elements you would have created. Okay, 75 elements you would have created. Okay, file close. Now once you do this, now you go for loads, define loads, apply structural displacement on key points. You first and the last key point you take and say okay, ux, uy, uz, rotation x, rotation y, you make it 0 and just say okay. Okay, then you force moment you go on key points, you take this, the first key point, no, there you have fy, as you know it is minus 15,000. Minus 15,000, you just say okay. Okay, then force moment on key points, next key point you take, then say okay, then it is minus 20,000. Minus 20,000 you'll say. Okay, now once you do all that, then you go solution, solve, current ls. Just say okay. Takes time. You wait, the solution is done message you should get. Solution is done message you got. Okay, now we are in the right track. Now general post process, that means pre-processing is over, solution phase is over. Now we have to go for the post processing phase. In that way, first you do this list results, you do first. Reaction solution, you just check if you're done correctly. Okay, you see here 12,500 and 22,500. That is node number 1 is this, node number 52 is this. Okay, 12,500 here, 22,500 here. What you got by theoretical methods is perfectly okay. That means you are correctly done till this. Now you go for element table. Okay, define table, add, by sequence number you do, SMISC 6 you go, and by sequence number SMISC 19 you go, apply, then sequence number SMISC 3 you go, then SMISC 16 you go. Let's say okay. This 6 and 19 will give us shear force diagram, and 3 and 16 will give bending moment diagram. Okay, just say close. Okay, then what you do is you go for this plot results, contour plot, line element results. You just see 6 and 19, you just say okay. Beautifully, you see here, this is 22,500. Okay, and this, as you know, this is 12,500. Okay, everything is matching with your theoretical result. Okay, this shear force diagram, if you compare with the theoretical one, what I've just now done, you just compare with that. This is 22,500, this is 12,500. It is perfectly matching with the theoretical ones. Okay, in the same way, you go for 3 and 16 bending moment diagram, you see. Okay, if you go for bending moment diagram, as you see here, it is at this, at red, here also it is increasing. At this point, it is maximum is 0.25 into 10 to the power of 8. That is what we have got, 0.25. Here it is 0.225 into 10 to the power of 8, 10 to the power of 8. Okay, this is 0.25, this is 0.225. These things are also perfectly matching with the theoretical ones. Okay, that is, to here it is 0.25, as you see here, almost what we had got is 0.25. Now it is 0.249. It is 0.25 10 to the power of 8. It is 0.225 10 to the power of 8. What you had got by theoretical one. Thank you for watching. Thank you.